Because we're using a framework of set theory to analyze probability, we can use our knowledge of unions, intersections, and complements to break down complicated events into compositions of smaller events for which it might be easier to calculate probabilities. An event that can be described in terms of the union, intersection, or complement of other events is called a compound event. We can get formulas for the probabilities of these compound events just as we did when we were counting the numbers of objects in these complicated events. We can derive these formulas directly from our counting formulas in the case of equally likely sample spaces. So recall that if E and F are events in a set or in a sample space, then E union F is the subset or the event consisting of those outcomes which are in at least one of the two subsets or events, E and F. So they're either in E or in F or in both. And E intersection F corresponds to the intersection of the subsets corresponding to E and F. This is the event consisting of the outcomes which are in both of the events E and F. And the complement is the event consisting of those outcomes which are not in E. It corresponds to the complement of the subset corresponding to E. So, for example, suppose we roll a pair of fair six-sided dice, one red and one green, and observe the pair of numbers in the uppermost space. And the sample space for this experiment is all pairs of numbers where the first one is 1 through 6 and the second one is also 1 through 6. So there are 36 things in this sample space. And if E is the event that the sum of the pair of numbers in the uppermost spaces is 7, then the elements of E lie along this off diagonal, and E is the set or the subset of S consisting of the pairs 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. And remember, this simple outcome 2, 5 is different than this one because we're talking about two different dice here. This would be 5 on the red and 2 on the green, and this would be 2 on the red and 5 on the green. And let's consider another event, the event that at least one of the numbers in the uppermost space is a 6. This event is the set of all pairs here with at least one 6 in them. So it might have 6 on the second, or 6 on the first, or even a 6 on both here. How many outcomes are in F? We have 6 here, plus 5 more, so the number of things in F is 11. And the outcomes in E intersection F are the outcomes which are in both E and in F. So they're everything in E which has the property that at least one of the numbers in the uppermost spaces is 6. This is in F, and this is in F. Those are the only two outcomes which are common to both sets. So you can see here that these numbers are the intersection of the two loops, and we have that the outcomes in E intersection F are 6, 1 and 1, 6. And how many outcomes in E union F? It's all of these 11 plus 4 more from E which are not in F. So we can use our inclusion-exclusion principle. The number of things in E union F is the number of things in E plus the number of things in F minus the number in E intersection F. And this is equal to, there are 6 things in E, there are 11 things in F, minus the 2 in the intersection. So that's 17 minus 2, which is 15. How many outcomes are in E complement? Well, this is all 36 outcomes minus the number of things in E. So the sample space here is playing the role of the universal set, and the number of things which are not in E is 36 minus the number of things in E, is 36 minus 6, which is 30.